Here's an example that's more like what you're going to see on an exam, not so much in the example, but in that the directions say to use any test to determine whether the series is absolutely convergent, conditionally convergent, or divergent. It'll be up to you to recognize what test would be appropriate for a particular series. Sometimes there's multiple tests you could use, and you'll get the same answer if you use any valid test. Here what I see is this sigma, or the sum as n goes from 1 to infinity of the quantity 1 minus n divided by 2 plus 3n, whole thing to the nth power. I want to use the root test, but notice that if n is bigger than 1, my numerator is going to be negative. So when we look at the root test, we do need to bring in the absolute values. This isn't like an alternating series where I can just dump the negative sign, right? So we've got the limit as n approaches infinity of the nth root of the absolute value of quantity 1 minus n over 2 plus 3n to the n. As before, the n's will cancel out, the n root and n exponent. And we have the limit as n approaches infinity of the absolute value of 1 minus n divided by 2 plus 3n. The way we're going to deal with the absolute value of 1 minus n is to recognize that our n is going to go to infinity. Our n is generally bigger than 1. If it's equal to 1, then 1 minus 1 is 0. Therefore, I'm going to drop the absolute values and then express the numerator as what I know to be a positive expression. So we have the limit as n approaches infinity of n minus 1 divided by 2 plus 3n, or I've taken the argument of the absolute value 1 minus n and expressed it as n minus 1 because I know that's going to be positive. Dividing by the largest power of n that appears in the denominator, we have the limit as n approaches infinity of 1 minus 1 over n over 2 over n plus 3, and as n goes to infinity, 1 over n and 2 over n both go to 0. That leaves me with the limit value of 1/3. We used the root test, you can see it, which means, and you can see it because we have the radical here, which means that the fact that our limit is less than 1 gives us that the series is convergent, but we were supposed to say whether it was conditional or absolute, and we used the root test. The root test, if it's convergent, is going to be absolutely convergent. That'll be the result. So the series is absolutely convergent by the root test. Moving on, same instructions. We're looking at the sum as n goes from 1 to infinity of the sine of n pi over 6 divided by 1 plus n times the square root of n. If we consider various values of n and the resulting expression sine of n pi over 6, let's just say n is 1, 2, 3, 4, 5, 6, that should be enough. Actually, those are not good at all. We're going to use n equals like 1, 3, 5, 7, and 9. If n is 1, the sine of pi over 6 is going to be 1/2. If n is 3, the sine of pi over 2 is 1. If n is 5, the sine of 5 pi over 6 is also 1/2. I know. Stay with me. If n is 7, the sine of 7 pi over 6 is negative 1/2. And then if n is 9, the sine of 3 pi over 2 is negative 1. Here's what we have. I just picked, some odd numbers just because they'd be easy to work with, I think. But we have 1/2, 1, 1/2, negative 1/2, negative 1. Some terms are positive, some terms are negative, but it's not exactly alternating. As you know, for the argument theta, say, the sine of theta is going to be positive if theta is between 0 and pi, but the sine of theta is going to be negative if theta is between pi and 2 pi. And so we're going to have this, kind of chunks of positive values and chunks of negative values, or clusters, I should say, of positive and negative values. We need to use the absolute values of the terms. So we're looking at the absolute value of the sine of n pi over 6 divided by 1 plus n times the square root of n. Now I don't see an exponent of n, so I'm not going to be using the root test. This doesn't seem like a great candidate for the ratio test because I'm going to end up with a weird funky sign expression here. So now I need to think about the other tests that we have. I don't want to integrate this. I may be able to get away with comparing this. Let's go there. What if I compared this to 1 over 1 plus n times the square root of n? Since in the numerator I have the absolute value of the sign, I know that that is never bigger than 1, and usually it's less than 1. So now I know that I have an expression here, the absolute value sine of n pi over 6 divided by 1 plus n times the square root of n is less than or equal to 1 over 1 plus n times the square root of n, which is less than or equal to 1 over n times the square root of n. And now I'm able to compare this to a p-series. Remember that n times the square root of n is the same thing as n to the 3 halves. And I know that this inequality is correct because 1 plus n times the square root of n is a larger denominator, and so would give me a smaller overall result than if I had 1 over n times the square root of n. Therefore, we're going to say since the sum, as n goes from 1 to infinity, of 1 over n to the 3 halves is convergent. How do we know it's convergent? Because it's a p-series with p greater than 1. The series, it's convergent, but we use the absolute values. And so the series is absolutely convergent by the comparison test. Okay, so there's our answer to this one. I do want to make one more note about absolute versus conditional convergence. If we have an alternating series, then we run the alternating series test. Always think about the alternating series test if you have an alternating series. The alternating series test will either fail because the limit is not equal to 0. If that's true, then it's actually divergent by the test for divergence. The alternating series test isn't the one that said it diverged. The test for divergence does. But if the limit is 0 and the terms of the series are decreasing, then we have convergence, right? So let's say the alternating series test says it's convergent. At that point, now I need to know, is it absolute or conditional? The way I'm going to find that out is to take like kind of what you just saw, the absolute values, and run whatever appropriate test works for the expression that you're looking at that point. So I think I can fix this diagram here. If it's convergent, then we use the absolute values and put them into whatever test is appropriate. Probably the integral test or some one of the comparison tests. Then if it's divergent at that point, but it was convergent from the alternating series test, that's when you're going to say it's conditionally convergent. If I run the test on the absolute values and I end up with a convergent series, then I can say it's absolutely convergent. And that's what you're going to kind of be looking at if you just have a mix of problems and you aren't instructed to use any particular test. If you notice you have an alternating series, then you need to know, hey, I need to figure out if it's convergent, I need to figure out if it's conditional or absolute convergence. And now that you've seen all of the tests, it's up to you to figure out which one is appropriate for any particular situation.